I'm again going to go with my statement that overall I was happy with the exams. If you've got questions, come talk to me. I've obviously made at least one mistake already. Somebody is wait. So keep an eye on me. This is where we were a week ago. Talking about rings with unity. And then we asked the question, if we look at everything except 0, do we have a multiplicative group? And the comment was about, I need inverses. And I said, well, okay, if you've got a multiplicative inverse, I'm going to call you a unit. Now, some rings have lots of units. Some rings have very few units. For a moment, let's go back and consider the ring of the integers. Standard addition, standard multiplication as a ring what's the multiplicative identity in that ring? One. So I want to know whether or not an integer has a multiplicative inverse. I want to know if there's something you can multiply that integer by to get 1. But that element needs to also be an integer. So really, I want to try and solve equations AB equals 1. The only requirement is that A and B are both integers.
Do 1 and 1 and then negative 1 and negative 1.
Are there any other integers that work? You pick any other integer, put it in for A, then try and solve for B, you're not going to get an integer, are you? You need a rational number. But, so the only units are plus and minus 1. But if I think about the rational numbers, what rational numbers have multiplicative inverses?
The entire set is used multiple.
As long as it's not 0, and remember it said up here we're using r star, so I'm not using 0. Take any non-zero rational number, multiply by its reciprocal, you get exactly 1. Okay, well, that's an important difference. In the integers, I only have 2 units. In the rational numbers, I have all of them being units. If every element of a ring other than 0 is a unit, we call R a division ring. Sometimes you'll hear the phrase skew field. I don't like that one as much, but it's mentioned in the book in passing. I want to make sure you hear the term, even if I'm not going to use it. The integers are a ring that is not a division, because not every element has a multiplicative inverse. Somebody name me another set, another ring, not of numbers, where this is also true. Klein 4 doesn't have any other operation. Klein 4 only has one operation. That's just a group, not a ring. So I need something that's got 2 operations in it, both of which are well defined. It makes sense, where some elements have inverses and some don't, for multiplication. Square matrices. Aha! So there's an example of a ring that is not a division ring. There's a fundamental difference between the ring of matrices and the rings of numbers when it comes to the multiplication. What's different for the multiplication in matrices? What's a fundamental difference in the way we multiply matrices as compared to the way we multiply numbers?
No, it's not, the direction you do it matters.
Order matters, it's not commutative.
Sorry.
Are full. A commutative division ring is called a field. That's why I didn't like using the term skew field for division ring, because field to me implies commutativity. Word skew, what's the word skew mean?
It's towards one, like skewed to one direction.
Pulled to one side or the other, right? It doesn't kind of jive to me. But if you were to think about the multiplication is pulled to one side, we can only do it in some orders, not maybe that, I don't like it. But non-commutative division rings, like the set of square matrices, are called strictly skew fields because of it. Again, a phrase I will probably never utter again. Yes?
So, quick question, do fields, the fields in physics, do they obey this mathematical definition?
Here's the problem. A field in physics is the expression of a vector valued function.
Correct.
Does the collection of vector valued functions obey this? Sometimes. Are they commutative? Well, no, because the cross product is a multiplication on vector valued fields, and it's not commutative. But the dot product is also a multiplication on vector valued fields, and it is commutative. I have too many operations for vector valued fields. So it's not the same sort of field.
Right.
Whew. Good attempt at a connection, and it's a good idea to start thinking about how I bring all of the other classes into this one, because the use of groups and rings in calculus is well beyond the scope of this course.
But we'll get close.
More questions? Z12 is a ring. Addition mod 12, multiplication mod 12. That's a ring. Does it have any units? Now, the thing that's missing is an intuitive understanding of what multiplication mod 12 looks like. That's, no. All right, wait a minute. I'm only looking at the numbers from 1 through 11, because units we never include 0. Multiplicative identity in Z12 is 1, so again, I'm trying to solve AB equals 1 in Z12. So what things can I multiply together in Z12 to get 1?
5 and 5.
Ah, because 5 and 5 is 25. 25 is 1 bigger than a multiple of 12. Five is a unit. There should be one unit that's obvious. Say again?
1.
1. 1 times itself, right? I'm going to make an incredibly, I hope, obvious statement. Unity should always be a unit. If you've got a ring with unity, it should be a unit. You have a multiplicative identity, it should have a multiplicative inverse itself. What else?
7 and 7.
What about 0?
Units can only come from the non-zero elements
Okay.
of the ring. So yeah, we're only looking at Z12 star, which doesn't include 0 by definition. There's one more. Yeah, because 11 squared is, which is 1 bigger than a multiple of 12. Now, I would point out to you something really weird happened here. Not only are all of these units, but their multiplicative inverses are themselves That's weird. What else is unusual about these four numbers? One is not a prime. Oh. It's the exception. One is not prime. But there are other primes in this set, right? 3 is prime. Why isn't it in this list? Which means not only are these numbers prime, they are relatively prime.
Co-prime and relatively prime are the same thing, right?
Yes. The term coprime is, I believe, slightly older than the term relatively prime. Maybe the other way around, but same idea.
Would that be the case for most units? Like one would hold true for a lot of them, and then the others would be relatively prime?
If m and n are relatively prime, is m going to be a unit in Zn? See if I can get there from here. But it turns out that in order to answer that question, I have to introduce another idea. Because I definitely want to answer that question. That would be a really nice way to find things, wouldn't it? All right, this is going to sound like a major change in topic. I promise it isn't. I would like you to solve 2 quadratic equations for me. I did say it was going to sound like a major shift. I've been doing this for a long time, Dr. Sassmore. Good, good.
Parentheses, x minus 2, x minus 3, so x is equal to 2 and 3.
And over there?
Factor out an x, so you have x on the outside, then x minus 1, x equals 1. 0.
There you go. Wonderful, marvelous, beautiful. There's only one problem. Because I stole this from the book, I don't want you to solve these questions in the integers. I want to solve these questions in Z6. I'll make it easy. Let's just look at the right one. Rather than do both of these polynomials, let's just try and solve x squared minus x in Z6. Now you might say to yourself, well, changing to Z6 doesn't change anything I did up there. That's absolutely still true, yes? Because I'm in Z6, and 6 is congruent to 0. I don't quite have the ability to draw the meme face. Huh? What the hell's going on here? Problem is the fact that in Z6, not everything's a unit.
Possible for that to have more than 4 solutions.
Well, the only other two numbers that are available are 2 and 5, right? And if I use 2, I get 2 squared minus 2, that's 4 minus 2, that's 2. If I use 5, I get 25 minus 5, which is 20, which is congruent to 2 mod 6. So it turns out, no, it has exactly 4 solutions. Yeah, I was going to say, I can keep going, but no, I'm only using 0 through 5.
But if it weren't Z6, they're like.
Well, I was going to say, we can do it in Z12, we can do it in Z19. We have, how many? Now, last time I checked, this sentence should piss a lot of people off. Which means being in Z6 did break something we did earlier. You did it automatically, Hayden, without even thinking about it. Because it's the right thing we were taught to do in every algebra class since we started doing algebra in middle school. You factored. And then you took each factor, set it equal to 0. Because if you multiply two things together and the answer is 0, one of the two things had to be 0. Not anymore, mother. of fact, in algebra class, we called it the zero factor property. If you multiply two things together and get 0, one of them must be 0. Nope. Throw that one right out the door. We're going to call these things divisors of 0. They're non-zero elements. That's why they're an R star. But when I multiply them, I get 0. I'll go back to the clock. What are some divisors of 0 in Z12? Because when I multiply them together, I get 12, which is 0 in Z12. So 2 and 6. What else?
3 and 4.
3 and 4. What else? There is no 12 in Z12.
Zero still work?
No, remember, they have to be non-zero numbers up there. The whole point is I'm taking two things that aren't 0, and I get 0 out.
Do 6 and 8.
I can do 6 and 8 because I get 48.
Four and 6.
Yep, because that gives me 24. I already have 6 on the list. Absolutely. There are at least 2 more numbers that we're missing.
Do 10 and 6.
Which adds 10 to my list,
9 and 4.
which adds 9 to my list. Okay, wait a second. 2, 3, 4, 6, 8, 9, 10. The ones I missed, what numbers are missing up there? 11, 5, 1.
7.
Divisors of 0 are the ones that are not relatively prime. To my modulus n. Now, believe it or not, you actually proved this, kind of. Because we were talking about multiplying in Zn in chapter 4, the Chinese remainder theorem. in solving linear congruences. I've seen this before. But let's prove it anyway. Means I got to do two proofs, right? If and only if. Which one are we going to do first? So, if A is a divisor of 0, I think that might be hard. So let's do that one. Well, we can do it after. We can also do it indirectly. Let's do that one after. So we'll start with the other one. Let's suppose that we had a number whose greatest common divisor wasn't 1. Well, let's call the greatest common divisor something. But that means that D divides N, right? That means that N over D is an integer. But wait, there's more. Not only is it an integer, it's strictly smaller than N. Because we're divided by something that's bigger than 1. Which means that's in Zn, not just Z. That's an integer smaller than N, and it's not 0. I don't know what it is, but it's some number in there, right? Oh, well then wait a minute. That means if I do A times that number, I get N. Or maybe some multiple of N, right? Wait a minute. That's congruent to 0 in Zn. Which means A is divisor of 0. I found the thing to multiply by that will give me 0. So I think, Colin, that the relative primeness is the key to doing the proof. So I think if I want to do the other direction, I should do it by contrapositive and suppose that the greatest common divisor is 1. And then show that it can't be a divisor of 0. Nope. Off the bottom of the page, that doesn't help. I want to show that this is not a divisor of 0. So if AX equals 0, that tells me that N divides AX. Wait a minute. N divides A times X, but N is relatively prime to A, so what does N have to divide? Got to divide X. It can't divide into A, it's got to divide to the other part. Wait a minute. If X is divisible by N, then X is 0 in Cn. So if I have A times something equals 0, the other thing has to be 0. It's not a divisor of 0. So divisors of 0 show up when I'm not relatively prime. Wait a minute. Wait a second. What if I'm working in ZP?
And each element only be, since each element would be prime, they'd only be divisible by themselves in one, right?
P itself is prime. The elements are everything less than that prime, right? So Z5, I've got 0, 1, 2, 3, 4. Z19, I've got 0 through 18. Those numbers are not necessarily prime, but the index is prime. The modulus, P, is prime. Think of Z5. 0, 1, 2, 3, 4. Non-zero elements, all of them are relatively prime. Because the only thing that divides 5 is 5s. Greatest common divisor of 5 in any of those is 1.
I mean, CP is a field, because all of the elements can be units.
None of the elements are zero divisors. And everything that wasn't a zero divisor was a unit. That's a field. I really should prove that everything splits into either units or zero divisors. But if you're going to be a unit, you need some other item to multiply to give you 1. And if there's another item that multiplies to give you 0, how do I get from 0 to 1? I mean, if we look at Z12, we just said that the divisors of 0, it was 2, 3, 4, 6, 8, 9, and 10. And then we said that the units were 1, 5, 7, and 11. And that's all of the numbers other than 0. One of the things we do often is try and figure out when I've got a field and when I don't. There's an example in the textbook about matrices whose entries are not real numbers, but instead are entries from a field. So I kept writing Mn of R, right? Where R was some ring, and that means I could do something like this. And I could think of matrices whose entries are in Zn. Oh, I'll use Zp primes, because that's a field. And that means that I could do matrix work in Zn, just like I do matrix work with real entries or complex entries. So those of you doing those eigenvector computations this week, the same thing here, but then I got to figure out the solving equations in Zp prime. We just saw sometimes that sucks. Determinants, reduced row echelon form, Kramer's rule, eigenvalues, eigenvectors, diagonalization, all the things we like to do for matrices work here as well. and are useful here, with two exceptions. Orthonormal bases and diagonalization fall apart here because the concept of length in ZP is all sorts of not possible. You think about the length of a vector, you take the square root of the sum of the squares, right? But square root of a bunch of integers might not be an integer. I'm in trouble. So it works, kind of. But the idea of lengths and the way lengths work, and the nice behaviors I get out of lengths don't work as well when I'm dealing with the n.
Never mind.
Okay. I'm good at never minding. I like that. Working on sets of matrices in other rings comes with its own sets of problems, but fields are better most of the time. Keep that in your back pocket. Blow Dr. McNabb's face out of the water when you go, oh, wait a minute, what if we changed fields? She's like, ah. All right. I started with the idea of trying to solve equations, right? We were factoring. But the other way to think about that is to think about canceling. Canceling is where you have the same thing on two sides of the equation, right? So I have like a plus b equals a plus c. And I throw away the a's and I get b equals c. I know that works. Why do I know that works? Because the inverses exist for the addition. The addition part is a group. Groups have inverses. But that means that for multiplication, I have a problem. And again, sneaking my way back into my linear class, it's a problem I've seen before. I can't cancel matrices because I don't know that they have an inverse. Because really, when I'm canceling, I'm multiplying by n inverse on the left of both. I'm multiplying by n inverse on the left of both sides of the equation. Can't do that if I don't have a inverse. Well, it turns out that's exactly when I have or don't have divisors of zero. If canceling works, can't have any divisors of 0. Why? I want to prove this. I need to figure out why canceling working prevents me from having 0 divisors. I have 0 divisors if I take 2 non-zero things and I get 0. So let's start there. Suppose in my ring R, cancellation works. And I have 2 things that I multiply together and I get 0. I want to show that neither of those are divisors of 0. Which means I need to show that one of them is 0. Because I wouldn't be multiplying 2 non-zero things together, right? Either A is 0 or B is 0. If they're both not 0, then I have a 0 divisor and I'm fucked. Because I'm supposed to have no 0 divisors. So pick one. Which one are you going to say is not 0? Without loss of generality, assume A is not 0. Then my goal is to show that B is 0. Well, if A is not 0, then A times 0 is 0, yes? Anything times 0 is 0. Transitivity. What does transitivity give me?
You can set those equal to each other.
Ah!
You can cancel.
Because that's what we said worked. Canceling worked. Canceling works. What's B?
0.
Hello. And since A was chosen arbitrarily to be something that I was selecting out of my ring, none of my elements can be 0 divisors. Unless I happen to pick A as 0. If A is 0, then B should be non-zero, right? Well, I can go through the same thing. If A is 0, I don't even have anything to prove. All right, wait a minute. That's one direction. What's the other one? What do I want to try and show here?
Suppose that R has no 0 divisors.
Aha. I want to prove that canceling works which means I want to prove AB times AB equals BC gives me B equals C. My eventual goal is to show that I can cancel. I should suppose one other thing in here, shouldn't I? I'm doing this, AB equals AC. I should suppose that A isn't zero, because you multiply it with 0 on both sides, you screw it up, right? How do I get from here to B equals C? Without just using the word cancel, because I'm trying to show that works. Yeah.
If A is not 0, does that mean we can? No, we can't. We can't like divide either side.
I don't know what division is. The only operations I have are multiplying and adding. I would like to eventually invent division. I don't have it yet.
You want to do something with the inverse? Like, say that there's an inverse somewhere in this universe?
I just know I have no zero divisors. I haven't proved yet that every element therefore is a unit. So I really don't know whether or not I can say, oh, clearly there's an inverse here. I still have to make that last step and say, oh, if you're not a zero divisor, you must be a unit. Let me go back to the properties of a ring we talked about a week ago. Addition, and the elements make a group. That means every element under addition has an inverse. An additive inverse, not a multiplicative inverse, which means I can subtract. I'm going to subtract. Now that makes me happy because I have a 0 on the right-hand side.
You factor out A, so you do A times B minus C equals 0.
Why am I allowed to do that, Reese? Why can I factor that A out?
Because in addition to the not used for it.
One of the definitional pieces of a ring is that the distributive properties work. Now I'm even happier because I have a 0 on the right-hand side, and on the left side I have multiplication. And I have no zero divisors. No, A is not 0. What does it tell me about the other thing?
Must be 0.
Otherwise we'd have a 0 divisor, right? And what does that tell you? Which is exactly what I wanted, just like I canceled. Check mark. Questions? Okay. If I'm in a ring that has no divisors of 0, let me think about this equation, ax equals b, with a not being 0. Can that have more than one solution?
Would it depend on what universe we're working in with that?
As long as I'm in a ring that has no divisors of 0, I've stated the critical piece of information. So if I don't have divisors of 0, can that have more than one solution? Actually, let me, rather than writing then, can this have more than one solution? Question. Let's actually try and answer the question. Now, what you could do is you could pick a ring that you know has no 0 divisors. What's a ring that you know has no 0 divisors? Any Z prime. So Z5, Z3 even, if you want a small example. And you could try and solve the equation. 4x equals 2. 2x equals 3. You could solve it for any coefficient of A, right? Again, we did that in discrete. And we figured out how to solve those. And when we did it, we found one and only one solution. It wasn't unless there was some weirdness about not being relatively prime. We already said not relatively prime means divisor of 0, and I don't have any of those. I think the answer is no. That you can only have one solution. How would I prove that?
Would you do it by trying to find a solution and showing that it's impossible to get one? I mean, I guess this is kind of it's exactly what proof by contradiction.
But I don't want to show that I can not get one. I want to show that I can't get 2. So let's suppose we had 2 solutions. So suppose I have 2 solutions and they're different. Somehow, somewhere, this is going to lead me to go, no, that's wrong. That's effed up. Wait, that contradicts something we said earlier. What can I do with those 2 equations? If I have no 0 divisors, canceling works. There's my contradiction.
You said they were different.
But they can't be because canceling works in this universe. Holy crap, wait a second. If I have no zero divisors, then AX equals B has a unique solution. And how do I get that unique solution? I have to have a multiplicative inverse for A, which means I have to have units. If I don't have divisors of 0, then I must have units, and that means I have a field. I have inverses. Which means well, no, wait a minute. It's not necessarily a field. Stop, scratch that. Why do I have to scratch that? This field requires one other thing that I didn't say anything about. Addition is abelian. It has to be commutative. And I didn't say anything about commutativity. As a matter of fact, I put my inverse on the left because A is on the left. I don't know that the multiplication is commutative. So I can't call it a field yet. So that's a unique solution. X equals A inverse B. So why don't I change the way I write that? Instead of writing A to the negative 1, let's write 1 over A.
I've just invented division.
But only for units. Division works in a ring that has no zero divisors and units. And if I want it to be written as B over A, it should be commutative, shouldn't it? I'm actually going to make this a definition. I'm going to call such a thing an integral domain. Division works in places like this. And it turns out that solving polynomials and factoring go hand in hand with being in an integral domain. Means I can factor polynomials in the integers while the coefficients are integers. What's the problem with trying to factor polynomials in the integers? Yes, but only in a very particular way. It doesn't always work. How?
Is that because sometimes you get answers that aren't necessarily integers?
I get resulting factors whose coefficients may not be integers. So an integral domain is kind of between a commutative ring with unity and a field. A field is where everything has an inverse. But this integral domain is kind of in the middle. Textbook. All right. I have lots of different kinds of rings. So here's my question. How do they relate to each other? Page 197, I have this picture. All right, wait a second. If this universe represents rings, I've got a really weird looking Venn diagram going on here. General rings here are on the outside. Rings with a unity, rings that are commutative. We know at least one commutative ring that does not have a unity. What is it? What would be in this piece number 4? Commutative ring, a ring where I can multiply in either order, that has no unity. To point out last week, it should.
You said without unity?
Yes,
2z?
the even integers. The integers themselves are a commutative ring with a unity. So that should be somewhere in the middle here, right? The question is whether that's here or here or here. Are the integers a field? Field is where everything is a unit, which means everything has a multiplicative inverse. The integers are definitely not a field because I can't take 2 times something and make it equal to 1. So they're not in the very middle. An integral domain is a commutative ring with unity that has no zero divisors in the integers. If a times b equals 0, what do we know about a or b? One of them has to be 0. So the integers actually go here. What goes in the field section that we've already talked about? There are at least 2 examples. Say again?
Z prime.
ZP, where P is a prime. What's my other example that we've mentioned today? The rational numbers. Rings with unity that aren't commutative. Where's a ring that has an identity, a multiplicative identity, where the order of the multiplication matters? Square matrices. So really the fun question is, what fits in 3? What fits out here? Those are the rings we haven't mentioned yet, have we? There's some weird going on here. You should put a post-it note or a bookmark on this page, page 197 in the book, to keep that in mind. Quite frequently, working in an integral domain is something we want to do because of the ability to factor, because of the ability to get nice results. But working in a field would be much more elegant. One of the big questions is, can I make fields? If I have a set I already like, can I make a field? But that's more of a discussion for next class, because I've run up against the clock. So I will see you all then. Have a wonderful rest of your day.